No.
Hello?
Hello?
Hello.
America!
Yeah.
Yeah.
Freak yeah.
I know, right? Anyway, improper integrals. I apologize for those people that spent too long on vacation and not come to school yesterday, and are missing out on their notes. So I'm going to do a brief intro to what we were doing yesterday for those people that weren't here because they were missing because they were having too much fun.
It's only Michael and Amy. Do you really care about them?
Hey, we don't say names
What-
here, okay?
Woodrow was not here yesterday.
Woodrow Wilson.
Woodrow was not here. I'm not saying his name.
Oh, oh.
He's
Okay.
not a Woodrow.
But I know. Was not here yesterday, right?
Jess.
Yes.
Sure.
Okay. All right. Anyway, so function is continuous on interval from a to infinity. Then from a to infinity, f of x dx is called an improper integral, as defined as we're taking, instead of we're going to infinity, we're taking the limit as that number goes to infinity. Okay. We're going to see if the limit exists. So now, provided the limit exists and is a real number, that's important. Okay. Then the limit as b goes to infinity of integration from a to b f of x dx exists is a real number, then the improper integral from a to infinity is said to converge. So it has to go to a number. If it goes to an idea, remember infinity is an idea, it's not a number, you can't put it on a number line. Okay? The limit does not exist, or if the limit is infinite, which is infinity, the improper integral is said to diverge. We're going to be divergent. Okay. The book's good, the movie's horrible. Super awful.
The movie sucked a lot.
Yes, very lot. Anyway, I hated the person they cast for the main character. No.
That wasn't anything how I imagined it should be.
No. Nothing like it. So yes, I was so disappointed. Yeah. She's gonna watch this video as she's actually looking for all the reviews of her acting and find this one here. Alright, if a function is continuous on the interval from negative infinity to b, then it's called an improper integral as defined. So we're going to take the limit as a goes to a negative infinity. Okay, that's going to be of my lower bound, provided that the limit exists, is a real number. Same thing. If it goes to a number or limit does exist, it's going to converge. If it does not, it is going to diverge. Okay, so bam, bam, bam. Where did we leave off here? Did you guys do 3?
We finished
Yeah, we did
example
example
3.
3.
Okay, all right. So this is actually important. Okay, converges if p is greater than 1, and diverges if p is less than 1. Now, think about the numbers in my denominator. The numbers in my denominator. So when I am doing this, so think about numbers that are greater than 1. So give me a number that p is greater than 1. Just give me a number greater than 1. 2! He said 2. So we're going to take a look at this, and we're going to say 1 over x squared. Is that going to converge or diverge? Converge. Because the number is greater than, that means that as this goes, it goes to infinity, right? That means the denominator is going to get bigger and bigger and bigger. So my number keeps getting smaller, smaller, smaller because I keep dividing it by more and more pieces. It's eventually going to go to 0. Okay? That one's going to go to 0. But now, if it's going to be less than 1, give me a number less than 1. 1/2. Okay,
Zero.
so,
Zero.
no, because 0 is going to mess up my thing. You know that, right? Okay, x to the, okay, negative 1. Okay, negative 1.
Wait, isn't it just X?
That's the point. All right, so if it's equal to 1, we just get, to the x, right? Okay, but if it is less than and it keeps going, then we're going to end up with, we keep going with that, so it's going to end up giving me this, which turns into x by itself, and then as we plug that into infinity, it's just going to go up to infinity, right? And so that will diverge, so it's going to infinity. Does that make sense?
Yes.
Okay, good. All right, so when it's not equal to p, so there is the proof here for this, okay, where it comes out to 2 different times where this one right here, this is going to be my this goes to infinity, so that's going to be divergent. And then this one over here, where it's not equal to 1, okay, so it's going to go as b goes to infinity, so we're going to have some numbers over here. So it's 1 over 1 minus t, whatever that number is. So it's the proof for this, how it works out. Okay. Okay, then if p is greater than 1, then p minus 1. Okay, p minus 1 is greater than 0. So this is the proof for this. So think about it. So p minus 1's got to be greater than 0. Because I moved it to the left-hand side, right? Subtract 1 both sides. Right?
Yeah.
Oh, okay. So you guys see where this is coming from, and you're not just playing on your phone right now, right? Okay. In the limit as b goes to infinity, okay, p minus 1, okay, p minus 1. So now, whatever the p is, minus 1, okay, has to be greater than 0. So that means that all of this right here is going to go to 0. So if it is greater than this, it's going to go to 0. So my denominator is always going to be bigger, right? As I plug in infinity, the denominator goes to infinity, so it keeps dividing it up. So it's going to be, that one's going to give me that it's going to converge, so I get to 0. And right here, note the area under the graph, y equals 1 over x. To the right of 1 is not defined. Okay? To the right of 1 is not defined. Okay, but the volume obtained by revolving the region about the x-axis is defined. Why is that? What's the integration of 1 over x? ln x, right?
Yeah.
Okay, what is ln of 0? Or I'm sorry, ln of 1? 0. So to the right of 1, but then what about left? That's going to give me some issues, right?
Mm-hmm.
Okay, so we're going to get a volume of that too. That is region, okay, as defined. It is defined there. Defined. There we go. Find the volume of the solid revolution of Gabriel's horn that is generated by a revolving region bounded by the graph, the x-axis, and to the right of 1 about the x-axis using the disk method. Okay, so we're revolving this, right? So it's good to sketch my stuff. I like sketching it. So we have something like this. We have from 1 to way over here. All right, so 1, and then way out here would be whatever my b value is. Okay, so the reason it's only going to go from 1 to the b value is why? Okay, right here, when I'm actually doing this, think about the graph. Think about the graph of 1 over x. Let me pull it up so you guys can see this, because if you have a mental image of it, it helps out. But if you don't have it, then I have to help your mental. All right, so control, divide, 1 over x. There we go. So we said because right here, as it goes to 0, right here, this is an asymptote, isn't it? It's going to be an asymptote that goes right here, goes up to infinity. But now, since this function right here is starting at 1, and why did I say it's going out to b? Will it ever equal 0? it's never going to equal 0, is it? Because it's going to have a horizontal asymptote at that. So it cannot equal 0 there. So it's going to have a horizontal asymptote. So we're going to go through and find, and we're going to rotate that using disk method. Okay, so I'm going to sketch. Like I said, I like my sketches. Something like that. I know, that's a horrible sketch, isn't it? Quit your whining. All right, so.
Supposed to write
It's like the
NTS.
asymptote is-
Huh?
Supposed to write NTS.
Not to scale?
Same with the slope.
Ah,
NFS.
I know,
Not-
right?
Not for sale.
Not for sale. Yeah, not to scale. Anyway. All right, so we're starting here, right? And we're revolving this. So if we're revolving this, I'm going to do disk method. So now, how do I set this up in disk method? Start with pi, right? Pi integral from 1. What's my upper bound? Infinity. But that's why I just wrote out to b, because I'm not going to, that's why it's not to scale, okay? And so now, what else, part of my disk method, what else goes here?
Yeah, radius squared.
Radius squared, right? So it's going to be 1 over x squared, and that's going to be dx. Yes? Okay, so this is going to turn into pi times the limit, right? As x, or in this case it's going to be b, goes to infinity of the integration from 1 to b of 1 over x squared dx. Okay? So let's keep going, right? So now, when I do this, what is going to be my integration of 1 over x? Or 1 over x squared, sorry. So it's going to be pi. So I have the limit as b goes to infinity of my 1 over, negative 1 over x, right? From 1 to b. All right, so now let's take the limit as b goes to infinity. What do we get? 0, right? So the top bound,
Sorry, negative 0.
so it's going to be pi times my top bound, which is going to be what? Negative 0, which is just 0, right? Thanks. Minus, now, lower bound is going to be what? Negative 1. So when I do that, so it's a minus the negative 1, which is going to give me a positive 1, right? So positive 1 times my pi, which is out front, means my answer is pi, and what are my units? Units cubed. Because it's a volume, right?
Yep.
Are we okay? Is this still decent?
Yeah.
Okay.
And then we would know that.
Yeah. All right. Integrate functions a to b that are not defined at an endpoint. Okay, so now if a function is continuous from a to b, so open a, close b, but is not defined at a, then from a to b, f of x dx is an improper integral, and then we have to take the limit of one side of that, right? Just the side that is going to be going to that. So now, think about it. If it's from a to b, and we're doing a, it's got to be to the right side of a, isn't it? But what if it was b that was undefined? It would be the left side of b, wouldn't it?
Yeah.
think about my lines right here. So if it would be like this, it's A to B, but now if it is A to B, right? It should be left side B, right? So it's going to be between those 2 points. So if I ever have those type of cases, oh look, there it is right there. B to the left side, improper integral, and these improper integrals sometimes called improper integrals of the second kind. It's like Close Encounters of the third kind. Okay, have finite limits of integration, but the integrand is not defined at one, but not both of them. Yes? So we could do this, but not at both, right? Okay, we could do it, but not at both. One, but not both. Okay. Okay, here's an example of it here. Okay, function continuous on a non-negative integral from a to b, close b. Then the improper integral a to b dx might be interpreted geometrically for the number t from a to t, where a is less than t and t is less than or equal to b. Integrand from t to b from f of x dx represents the area under the graph of y equals f of x from t to b, shown in the figure right here, as t goes to the right side of a. This approaches the area under the graph y equals f of x from a to b, shown in the figure, blah. Alright, that is from a to b, f of x dx converges. Its value is defined in the area from a to b. So it has to converge. If it does not converge, can't do it, right? Can't find the area. Alright, so there we go, right there from t on this side right here. And so, yeah, okay. Determine if the area under the graph of y equals 1 over rad x from 0 to 4 is defined. Which one is undefined?
That's less than 1.
Okay, so this is going to be from 0 to 4, right? Yes?
Right.
Okay, so it's going to be from my integral from 0 to 4, 1 over x to the 1/2 dx, which is going to turn into the limit as a... No, I'm sorry, x approaches, sorry.
T approaches right side.
Yeah, so it's going to be t approaches a to the right of the integral from a plus to the 4, and that's 1 over x to the 1/2 dx. All right, let's go ahead, integrate. So it's going to be a mean. So limit as t goes to a from the right of, what's that going to give me? Isn't that going to be x to the negative 1/2? Yes?
Yeah.
Same thing. Now take the integral, so it's going to be positive 1/2, right? So it's going to give me 2x to the positive 1/2. And that's going to give me from a plus to 4. So let's take a look. And
Wouldn't the lower bound be t?
yes, it would be. I'm sorry. Why did I keep saying a plus? I was from the... You're right. Sorry.
And then up there. No,
No.
that's good.
Why did I... No. Yeah, so it should be 0 to the positive. Thank you. There we go. 0 from the right hand side, right? And this is t. Alright, so from this one right here, so now can I do this one now?
Yeah.
So the top is going to be, that would give me what? Let me see, 2, 4. minus the lower. Now, when we do this, now can I plug in 0 here? What's the square root of 0? Times 2? You notice what happened there. So when I was able to take the integral of my function, it no longer was going to be undefined at 0, right?
Yeah.
That's what he was talking about earlier when it said that you could actually have a function that's undefined, but when you take the integral of it, it's no longer undefined.
Yeah.
Make sense now?
Yeah.
So my answer here is just going to be 4.
Units squared.
Area? Yes. Units squared. All right. That's example 5. Let me see how many's left. There. 7, 8. Okay, it goes to 8. We'll finish this today. 9th hour. Like, share, subscribe.